Hi. So, welcome to this video lecture where we discuss the underdamping, overdamping, and undamped SHM or simple harmonic motion oscillations for a second order linear ordinary differential equation. So, in the previous videos where we had already figured out what the solution of a general second order linear ordinary differential equation is going to be. So this is the solution. This is the differential equation with zero input or no external force whatsoever. Just to remind all of you that this is modeled on this problem where you have suspended a mass from the ceiling by a spring, and all of these are the forces which are acting on it, and if you translate them into an equation, this is what you get, where B here, this constant B represents the resistance, air resistance, or the friction while this body is moving up and down, and C here represents the strength of the spring or the stiffness of the spring constant. Actually, the spring constant is K divided by M, and that is C. So this is what we had figured out in the previous videos, that general solution for an equation of this kind will be C1, some constant, times the first solution, which is e to the power m1t, and another constant times e to the power m2t, where m1 and m2 are roots of the auxiliary equation for this differential equation. So auxiliary equation, all the different differentiated terms are replaced by m. This is differentiated twice, so you have an m square. This is 1, so we have m here. This is not differentiated at all. There's a slight problem here. There's an x. There will be x. So x is not differentiated at all. So this is m to the power 0 or just 1. Okay. Right. Now, of course, m1 and m2, if you solve this quadratic equation in M, you will get, depending on the values of B and C, you will get the two roots, M1 as this and M2 as this, where M1 takes the positive square root and M2 takes this positive square root. That's just how I have named them. All right. So, as I had mentioned in the previous video, that depending on what B and C are, or how B and C are shaped, you can have various cases. One of the cases, or actually the two cases that we will discuss in this video, are the cases of underdamping and overdamping. The underdamping happens when this term, this discriminant term, b square minus 4c, that is negative. In other words, this is an imaginary number, square root of a negative number. That's the case when you have what is called an underdamping. The case where b square is greater than 4c, in other words, m1 and m2 become totally real numbers, then that's the case of overdamping. And in the case of the underdamping, there's a sub-case where b can be 0. So b is less than 4c, it can all the way go up to 0. Okay, so at the value 0, there is no damping, so the case therefore reduces to what is called an undamped SHM. So undamped means there is no damping, no air resistance. B0 means this is the air resistance or friction, no damping, but simple harmonic motion, just up and down motion for this body suspended by the spring. All right, and in these two cases there will be damping. This is damping, but it's underdamped, as in there will be oscillation for quite some time before the body comes to rest. Overdamping is it's overly damped. There is too much resistance, too much friction, so it does not go up and down for very long. You give it a pull, you let it go, it immediately comes to rest. Okay. And the case of critical damping or resonance where b square is equal to 4c, we will discuss that in one of the later videos. So let's discuss one of them. Let's go all of them one by one. So underdamping and overdamping for today. Underdamping. So let's just leave only the problem and the solution, the general solution up there, and we discuss the case of overdamping for the moment. Okay. Sorry, underdamping. We discussed underdamping. Okay. So as I said, underdamping happens when b square is less than 4c. If b square is less than 4c, then m1, which was minus b by 2 plus root over b square minus 4c by 2, this will be a complex number, as I said. So this will be a pure imaginary number, okay? Because it's a root over a negative number. So let me call this number a purely imaginary number. Let me call that I omega, okay? Omega will turn out to be the frequency with which this body oscillates. So, and you all know that omega is the notation that is used for frequency. And just to simplify our notations, I don't want to keep on writing b by 2 all the time. I'm just going to call b by 2 as r. Okay. So, in other words, what we have, so r is b by 2. And this I omega is root over b square minus 4c by 2. Similarly, m2, which was the negative, which had the negative square root, will become minus r, or in other words, let's just write that down for, so this is root of b square minus 4c by 2. This will be minus r minus this quantity, which is I omega. So in other words, m1 and m2 are complex conjugates. Okay, so m2 is a complex conjugate of m1. Okay, right. Now I just want to mention here that these r, omega, the b and c are actually all positive numbers. We are taking them to be positive because they are positive from the problem that we have modeled. B here is just eta by m. Eta is the resistance constant or the frictional constant, which is positive. M is mass positive. Similarly, k by m is c. K is the stiffness, a positive number. M is mass positive. So everything is positive. So we're just dealing with, you may have negative numbers thrown in once in a while, but for the moment, the problem that is the model on which the problem stands makes all the B and C are positive. So therefore R is positive, omega is also positive. Okay. Now let's therefore solve the case. Okay. The general solution is this. And we know what is M1 and M2. They look like this, complex conjugates. So I can substitute for M1 and M2 these two values. And let's try that. So my objective is to find the general solution for this. And what we do, therefore, in this case, in the case of underdamping, where this is the criterion, we have the general solution as C1 e to the power, well, for M1, I want to write this, minus R plus I omega, and then there is the T, plus C2, the second constant, e to the power, well, M2 is minus R minus I omega, sorry, the minus comes inside the brackets, T. Well, I can break this up as e to the power minus R into e to the power minus I omega t. This, you can do that's the same thing here, e to the power minus R into e to the power minus I omega t. I can take out e to the power minus RT common from both of these terms. So I'm left with C1 e to the power I omega t plus C2 e to the power minus I omega t. Right. And, well, I can simplify this a little bit more using Euler's identity of exponential with an imaginary, purely imaginary index. So, e to the power minus RT, as all of you would recollect, that e to the power I omega t will be cosine omega t plus I sine omega t, and then the second constant will multiply e to the power minus I omega t. So you will have cosine omega t negative, a minus for this minus, I sine omega t. Right. Can I group the cosine terms and the sine terms? So I have e to the power minus RT. If I group them, I have, for the cosine omega t term, I will have C1 plus C2. So C1 plus C2 will be a constant. It's a constant because it's an addition of two constants. So that goes with cosine omega t. And what goes with sine omega t? An I for both of them. And then C1 minus C2 for this minus sign. And then that goes with sine omega t. Well, because these are constants, so I don't want to keep on writing them in this form. I just write them in a much more, in a more simplified form. I just want to give them different names. I want to call this m, this first constant, and the second constant n, sine omega t. Right. So that's the general solution. That's the form of the general solution in the case where there is underdamping or b square is less than 4c. Right. Now, what does this tell us? What does this solution signify, or what does this imply so far as the movement, the physical movement of this system is concerned? Well, what it does is, so if I just plot somewhere here, I can do it. I have some space. Let's just say I plot the solution and I plot time. So this is x defined as a function of time. So I'm plotting time with on the horizontal axis, and I'm plotting xt, which is the displacement of the body, along the vertical axis. Well, what this is telling us is that this will behave, if you forget this for a moment, this is, it's a wave. It's cosine omega t and sine omega t with two coefficients. So it's an oscillation, up and down movement. However, it's multiplied by a number, which is the amplitude. So that tells you how much the wave is going to go up and down, how much it is going to oscillate, how much the body is moving up and down. That is given by this amplitude. Now, it turns out the amplitude is a function of time with a negative sign in front. So this is a positive number. So this makes it a decaying term. So because this is e to the power minus RT, as time goes on, this term decays, or it reduces. It reduces more and more and falls towards zero. So even though the body is moving up and down according to what this is telling us, according to this function, the oscillation, but the amplitude of the oscillation will decrease. It is going to decay because of this amplitude term, which is a function of time. So that's exactly what we come to. So it starts with, at time t is equal to 0, it starts with a certain displacement. At t is equal to 0, this is 1, this is m, and this is 0. So at t equals 0, your x0, xt, if you put t all through, you will get m. Okay, so this is your m, the initial displacement. Okay, wherever you have pulled this to, the initial displacement is m. And then, as it says, that this will move up and down. So xt will follow an oscillation, but the amplitude will keep on decreasing. And finally, as you increase time, as you let it go on and on, as time goes to infinity, the amplitude is going to be 0. So in other words, the oscillation is going to get lesser and lesser in its amplitude, and it is just going to settle down at one point. It's going to come to a standstill. That's what it means. Okay. There was the case of So as a sub case of underdamping, I told you that B, what if B is, obviously B squared is less than 4C. What if B goes down all the way to 0? Then that's the case of undamped SHM. Okay, that's the sub case. It's the case of undamped simple harmonic motion. That's the case when not only is B squared less than 4C, B is actually equal to 0. That's the case when B is 0. So what happens if B is 0? So if B is 0, of course, then again, everything remains the same. This is still a purely imaginary number, because then you have the square root of minus 4C by 2, which is the square root of a negative number. So you still call it I omega. Everything remains the same, except that here, if B is 0, R is 0. Correct? Because R is B by 2. So in the final solution, the term that depends on R will get the 0, because R is 0 here. So e to the power 0t is just e to the power 0, which is 1. So therefore, in the case when the air resistance or friction, there is no friction, that is the term that is responsible for the friction. If that is 0, then this solution says it's going to be just a simple harmonic motion up and down. It's an oscillation, but without any undamped or undecaying amplitude. So the amplitude is not going to decay. It's just going to go on and on and on for the rest of time. And so it's just going to start at M. It is just going to go on with the same amplitude. And that's the simple harmonic motion, but undamped. So not reducing at all. All right. Okay, very good. Now we come to the case where it is overdamped, where the resistance is just too high. Okay. When B square is greater than 4C. In the case where, so we're now discussing overdamping. Overdamping when B square is greater than 4C. So the resistance is too high for the stiffness. C is responsible for stiffness. In that case, so not this anymore. In that case, B square minus 4C is now a real number. Well, the square root of B square minus 4C, it's a square root of a positive number, so it's a real number. So there is no need for this I here anymore. Okay. So this is just going to be, I'm just going to call this huge number here omega, because I don't have to put the I, because it's not an imaginary number anymore. So M1 and M2 are just going to be what they are without the I. Okay. Well, in that case, what's the solution? Well, everything remains the same, except you don't get the I. You don't get this I. This is as it is. You don't get this I. You don't get this I. Okay. And so now, because these are just exponential, well, I can't now, sort of turn this into cosine and sine. The Euler's identity does not apply here, because it's no more, the index is no more imaginary. So I'm just going to rub this out. Okay. I'm just going to rub this out. So, in fact, this is what it is. Okay. Well, if you take this a little bit further, actually, if you take this inside, you have C1 e to the power minus R plus omega t. Well, we already have that written out there. Sorry. I just that's what it comes from. Okay, so let's just forget this. Okay, we come to exactly how the solution looks. Okay, just replace m1 by this and replace m2 by this. Okay, let's analyze these two indices here. Well, what is minus r plus omega? Is this positive or negative? It is a negative number because r here is b by 2 and omega is square root of b square minus 4c. So this is a positive number. So b square minus 4c is less than b square. And if you take the square root, that would be less than b. So the numerator here is less than b. And the denominator is 2 in both the cases. So omega is less than r. So omega is less than r. I hope that's clear. You're subtracting something away from b squared. So this quantity is less than b squared. Take a square root, it's less than b, which is less than this numerator. So if omega is less than r and you take r to this side, you will have minus r plus omega less than 0. So this is a negative quantity. So it's a decay. As time goes on, this quantity, this function is going to fall. It's a decaying term. Similarly, this is negative because both r and omega are positive. So this is the negative all through. So this is also a decaying term. So this function, in the case when b squared is more than 4c, the function is a decaying function. It falls. So at x equals 0, t equals 0, the initial displacement, how much is that? Well, it's c1 plus c2. Okay, so let's just analyze this graph now. Well, it's a very easy graph in the sense that it starts at a displacement of c1 plus c2, okay, because if you put 0 instead of t here, this is going to be 1, this is going to be 1, so x at 0 is c1 plus c2. So if I draw the graph of this function, this solution now, in the case of overdamping, if this is time again and this is the displacement of the body, then at 0 it starts at some point which is called c1 plus c2, and then because this is a decaying function and it's all positive because exponentials are positive numbers, c1, c2 here, well, they can be negative, c1 and c2, we don't know. So depending on what c1 and c2 are going to be, if they are positive, it's just going to fall and that's it. It's just going to fall. Nothing is going to happen more because both are decaying functions. So this function is just going to decay more and more. Well, if depending on what c1 and c2 are, if one is negative, but it's a big negative number, it can sort of fall once here and then go up and then sort of line up with the 0 at, whatever it is, it's just going to so in this case, it's just, if you pull it down to its initial position at time t0 and you let it go, in one case, it can just go up and then stop because that's what it's saying, it's just decaying. Or in another case, depending on what c1 and c2 are, it may just go up once and then come down and stop. So it's overdamped. It is not going to oscillate much. It's going to be very small oscillation. For example, if you think of the spring being a very loose spring and you're hanging this inside some liquid where the resistance is too high, so you just let it go, it goes up and then it stops. It doesn't even go up and down. So that's overdamping. So the resistance from the fluid or the friction in the fluid from the fluid is just too high. Okay, that's the case of overdamping. All right, so this actually finishes these two important cases where I just want to mention here that in the case of underdamping, the two roots m1 and m2, they were complex numbers, okay, because b square was less than 4c. Also in the case of undamped, because B square was 0. So that was simple harmonic. Okay. So over there also, so B square was 0 means, B was 0 means the real terms were 0. So M1 and M2 were again complex. So in the case of underdamping and undamped SHM, in these two cases, M1 and M2 were both complex numbers. In the case of overdamping, where B square is greater than 4C, so M1 and M2 are real numbers. Okay, because now this is square root of a positive number, square root of a positive number. So M1 and M2 are real numbers. We will discuss the case of resonance in the next video. In the next video, because B square is equal to 4C, where the resonance cases or the critical damping cases when B square is equal to 4C. In that case, M1 and M2 will be real because then this will be 0 and this will be 0, but they will be equal. So in the case of critical damping, just want to give a note here, critical damping, which we will take up in the next video, critical damping or resonance, that's the case when B square is equal to 4C. In this case, so this is 0 and this is 0, so they're both equal but real because B is real. M1 and M2 are real, but M1 is equal to M2. This we will take up in the next video. Very interesting case. Alright, so much for this video. We will take this up in the next one. Thank you.